The James Webb Space Telescope, humanity's most advanced eye in the cosmos, has once again amazed astronomers and the public alike, this time by dramatically reshaping our perception of Pluto. Once thought to be a frozen relic at the edge of the solar system, Pluto is now revealing itself as a far more dynamic and intricate world than previously believed. Thanks to JWST's unprecedented infrared vision, Pluto has stepped into the spotlight not as a lifeless, icy outpost, but as a complex celestial body full of geological, chemical, and possibly even biological potential. Once considered little more than an icy speck orbiting in deep space, Pluto now appears as a vibrant world teeming with unexpected activity. Central to this revised understanding is JWST's ability to see in the infrared spectrum, a capability that has enabled scientists to peer through Pluto's frigid surface layers and uncover details previously invisible. These observations have exposed a rich and diverse surface composition, dynamic atmospheric behavior, and even hints of a subsurface ocean beneath its icy shell. One of the most intriguing regions on Pluto is Sputnik Planitia, the vast, heart-shaped plain that has captivated observers since the New Horizons flyby in 2015. Originally thought to be nothing more than a nitrogen ice basin, new insights suggest it might conceal a liquid ocean beneath its crust, kept warm by residual heat from Pluto's rocky core. This possibility brings with it profound implications. If such an ocean exists, it could be a stable, long-term habitat for microbial life. The notion of a hidden ocean beneath an ice-covered world may sound far-fetched, but Earth itself offers analogs. Life has been discovered in extreme environments, such as hydrothermal vents on the ocean floor, where sunlight never reaches. In these deep-sea realms, chemical energy sustains entire ecosystems, offering a model for what might exist below Pluto's frozen surface. Pluto's terrain, too, defies expectation. Gigantic ice mountains, some as tall as the Rockies, rise above flat plains. These features suggest geological processes are ongoing. Unlike the static, unchanging worlds we once imagined in the outer solar system, Pluto appears geologically alive, reshaping itself through cryovolcanism, tectonic movement, or slow-flowing glaciers of nitrogen ice. Scientists believe that the slow decay of radioactive materials within Pluto's core could be responsible for the internal heating driving these surface changes. This thermal activity may gradually warm the surrounding ice, leading to subsurface motion and occasional surface eruptions, features once thought impossible on such a distant world. In this way, Pluto joins the ranks of other ice-covered worlds like Europa and Enceladus, places now seen as some of the most promising locations for life beyond Earth. These moons of Jupiter and Saturn have captivated scientists due to their subsurface oceans, and Pluto, once written off, may be equally worthy of exploration. Pluto's unique relationship with its largest moon, Charon, adds another layer of complexity. The two objects are locked in a gravitational dance, orbiting a shared center of mass in a perfect balance. This mutual orbit creates tidal forces that stretch and flex both bodies, potentially contributing to internal heating that sustains geological activity. Charon itself is no bystander. It exhibits massive canyons, scarred tectonic regions, and mysterious reddish patches near its poles. These areas may be coated in tholins, organic compounds formed through chemical reactions driven by solar radiation. Some researchers believe that chemical materials may be exchanged between Pluto and Charon, making their connection more than gravitational. It could be biochemical as well. All of these revelations are possible thanks to JWST's cutting-edge technology. While the New Horizons spacecraft provided stunning imagery during its brief flyby, the Webb telescope offers the chance to monitor Pluto over time, analyze its chemical makeup, and study its atmosphere in far greater detail. Webb's observations have uncovered an atmosphere rich in nitrogen, methane, and carbon monoxide, gases that behave in remarkable ways as Pluto travels through its lengthy orbit around the Sun. As Pluto nears its closest approach to the Sun, perihelion, surface ices sublimate into vapor, forming a temporary atmosphere. As it retreats, these gases refreeze and settle back down, creating an atmospheric cycle unlike anything seen elsewhere in the solar system. This ever-changing cloak of gas forms hazy layers that stretch high above the surface, creating a complex and stratified atmosphere. These hazes are made up of particles formed when solar radiation breaks apart methane and other molecules, which then recombine into more complex compounds, including the reddish tholins seen on the surface. Tholins, in particular, have captured scientific attention. On Earth, similar organic molecules are thought to be the precursors to life. Their presence on Pluto suggests that essential chemical building blocks might be forming there naturally, in conditions far colder and darker than those on Earth. This raises the compelling possibility that the earliest steps toward life might not require Earth-like warmth or sunshine. Researchers are now deeply focused on how these organic molecules might interact with water ice beneath Pluto's crust. Could these compounds, in the presence of liquid water and energy from internal heating, give rise to basic life forms? While no direct evidence of life has yet been found, the potential for prebiotic chemistry is stronger than ever before. Perhaps one of the most astonishing insights from Webb's data is the thermal variability across Pluto's surface. Certain areas appear warmer than others, potentially indicating heat rising from below or the presence of geothermal hotspots. Subtle movements in the crust suggest ongoing tectonic or cryovolcanic activity, adding further support to the idea of a dynamic interior. Public interest in Pluto has surged as a result. The dwarf planet, long overlooked, is now the focus of mission proposals and scientific excitement. Ideas are being floated for orbiters that could map its terrain in detail, landers to examine its surface chemistry, and even submersibles designed to melt through its icy shell to explore any hidden oceans. These futuristic missions could search directly for biosignatures, chemical evidence of life, or reveal entirely new classes of geological and chemical phenomena. Scientists are developing heat-propelled drilling probes, lightweight aircraft, and even robotic submarines capable of surviving the harsh conditions below the ice. But the James Webb Space Telescope's contributions to our understanding of Pluto go far beyond simply classifying it as a geologically active world. In fact, JWST is reshaping how scientists perceive Pluto, not just as a distant dwarf planet on the outskirts of our solar system, but as an active participant in a much larger and interconnected cosmic ecosystem. This revised perspective elevates Pluto's status from an isolated, frozen body to a dynamic world that interacts constantly with its surrounding space environment. One of the most fascinating aspects of this interaction involves space weather. Unlike Earth, which benefits from a strong and protective magnetic field that shields it from solar radiation and harmful charged particles, Pluto is not so fortunate. It lacks a significant magnetosphere, leaving it vulnerable to the relentless influence of the solar wind, a continuous flow of charged particles emitted by the sun that travels billions of kilometers into space. Despite Pluto's vast distance from the sun, the solar wind still reaches it, bathing the dwarf planet in streams of energetic particles. When these solar wind particles collide with the molecules in Pluto's thin and tenuous atmosphere, composed mainly of nitrogen, with traces of methane and carbon monoxide, they initiate a series of complex interactions. These collisions can ionize the atmospheric gases, breaking apart molecular bonds and triggering new chemical reactions. The resulting interactions can produce exotic compounds, including tholins, reddish organic substances that have also been detected on Pluto's surface. These tholins are thought to form when solar radiation or cosmic particles bombard methane and nitrogen, leading to the creation of complex, carbon-rich materials. On Earth, tholins and similar organic molecules are considered potential precursors to life. JWST's infrared instruments have enabled scientists to observe these atmospheric and surface changes in detail, revealing not only the presence of these organic materials, but also their ongoing formation processes. This active exchange between Pluto's surface, atmosphere, and the broader space environment suggests that Pluto is not a static or dormant object, but is chemically evolving over time. The dwarf planet's exposure to cosmic forces, combined with its internal and atmospheric dynamics, makes it an unexpectedly rich laboratory for studying the interactions between small planetary bodies and the vast, energetic processes that govern our solar system. Remarkably, Webb has detected emissions from these interactions. When solar particles collide with Pluto's atmospheric gases, they can trigger ionization and complex chemical reactions. These reactions can fragment methane and nitrogen molecules, allowing them to recombine into new compounds, some of which are the very tholins found on the surface. This ongoing chemical exchange means that Pluto's surface is not static, but is being continuously modified by space weather. The reddish tint in some regions, including Charon's North Pole, may be a result of this energetic bombardment. Pluto's path through the Kuiper Belt also plays a major role in shaping its environment. This vast ring of icy debris, remnants of the early solar system, is home to many small bodies and dust particles. As Pluto travels through it, it encounters micrometeorites, charged particles, and cosmic dust that can erode its surface, add new materials, or initiate chemical layering. These interactions, subtle over short timescales, have likely shaped Pluto's appearance over millions of years. Webb's sensitivity allows astronomers to detect these small-scale effects and understand how they influence Pluto's surface evolution. The combined effect of these external forces challenges the idea that Pluto is a distant, passive object. Instead, it is actively participating in its environment, absorbing energy, reacting chemically, and possibly preparing the stage for life. The implications of this extend beyond Pluto. Other objects in the Kuiper Belt, like Eris, Haumea, and Makemake, might also harbor subsurface oceans or complex chemistries. If one distant world can possess life-friendly features, then many others might as well. This new understanding is sparking fresh debate about Pluto's classification. Since being demoted to a dwarf planet in 2006, Pluto's status has remained controversial. Now, with mounting evidence of geological activity, an atmosphere, organic compounds, and potential for water, many scientists are calling for its reclassification. The debate is not just about terminology. It reflects the evolving nature of scientific knowledge. As our tools improve and our understanding deepens, so too must our definitions and frameworks. Pluto stands at the forefront of that change, pushing us to rethink how we categorize worlds. Moreover, the investigation into Pluto has united scientists from diverse disciplines. Geologists, chemists, biologists, and physicists are collaborating like never before to explore this icy world. Organic chemists simulate Pluto's surface reactions, geologists model its interior dynamics, and astrobiologists theorize about life in frigid oceans. This multidisciplinary approach marks a new era in planetary exploration. Beyond academia, Pluto's resurgence has captured the world's imagination. Students draw its heart-shaped planes in classrooms. Documentaries bring its discoveries to living rooms, and space enthusiasts debate its planetary status in forums and online communities. Pluto has re-entered the cultural conversation with force. This public excitement has tangible consequences. It encourages funding for deep space missions, sparks international cooperation, and attracts private investment. Agencies across the globe are now considering cooperative missions to explore Pluto more thoroughly. Webb's findings serve as a reminder of why exploration matters, not just for knowledge, but for inspiration, unity, and the timeless human drive to understand our place in the universe. Pluto's story is no longer one of exile. It is one of rediscovery, resilience, and revelation. With each discovery, we edge closer to answering one of humanity's oldest questions. Are we alone? Perhaps, in the icy depths of Pluto's hidden ocean or the red-stained valleys of Charon, the first clues await. And as long as we continue to reach beyond the known, guided by instruments like the James Webb Space Telescope, we will keep uncovering the wonders that lie just beyond the edge of imagination.